Welcome to the MOOCs course Mechanical Unit Operations. The title of this lecture is Size Analysis by Screening. We have seen in the previous lecture how to do the screening, what are the other basic concepts about the screening. What we have screen is a kind of metal pan with forming bottom as screens. Whatever the screens are there, they form a bottom of a metal pan, and then those metal pans having screens at the bottom can be arranged one onto the other. So, we arrange them in such a sequence that at the bottom most finest screen would be there, or the screen which with the smallest opening would be at the bottom, and the next smallest would be on the top of that one. Like that, gradually we can arrange the screens one on the other, and then at the top we will be having a screen which is having a opening largest compared to the all other screens. So, then whatever the crust material is there, that will be keeping on the top screen, and then we will be mechanically agitating it or vibrating it for 20 minutes or 30 minutes. Then based on the size of the material, the particles may be passing through some of these screens and then retaining on some of the screens. So, based on the size, each screen may be having some amount of the material being collected on individual screen, right. And then these screens are arranged in such a way that in this particular way we name them as a screen increment. Screen increment numbering we do at the bottom one is will be giving I is equals to 1, then I is equals to 2 is the next above it, and like that the topmost one would be given the I, the largest number of the whatever the total number of screens we have. Let us say we have 20 screens in the stack, then I would be 20 for the top one, like that, right. Then whatever the material collected individual screens will be weighed, taken out, weighed, and then the mass is reported, or the mass is converted into the mass fraction by dividing the mass of the total entire sample that has been taken as a feed. Then the average size, we have assigned a kind of average size for the material that is being retained on each individual screen. So, let us say on screen 2 whatever the material is retained, the average size of the particles of that particular sample retained on the screen increment of second screen. So, that would be the size opening, the average size would be the arithmetic average of the screen aperture of screen 2 plus screen aperture of screen 3 divided by 2, like this. Increments we give from bottom to top. So, then accordingly we have to do. So, now in this process, that whatever the average diameter is there, that against to the mass fraction of the material or mass of the material retained on that particular screen, we tabulate them. This is how we do the screen analysis and then tabulate the experimental observation. So, the important thing here what we see, the screen opening, right. Screen opening is a kind of, screen aperture is a kind of very much important factor. So, we should have a kind of some kind of standard screens which can be used with a kind of proper reference. So, are there any standard screens or not, that first we see, and then from there we go to the analysis, size analysis, finding out the different equivalent diameters for the samples, and then surface area for the individual fraction, and then specific surface for the entire sample, etc. Those kind of things we do. So, in order to do this one, we need to know this screen opening. So, for that we have to see what are the types of standard screens are available. So, Taylor screen series is the kind of one of the standard one, right. It has been developed or designed based on the opening of the 200 mesh screen, which is established at 0.074 mm. So, 200 mesh screen in the sense, let us say this is the screen, this is the screen that you have. So, out of which let us say this particular dimension is having 1 linear inch dimension. So, with 1 linear inch dimension we will be having 200 openings like this. So, then that particular screen is known as a kind of 200 mesh. Like that you can take anywhere linear dimension 1 inch, that also if you see that will be same, right, in any one direction, like that any location if you see. So, per linear inch dimension of that particular screen there will be 200 openings. So, the diameter of that particular opening screen aperture is 1 by 200 minus dia of the wire that has been used for this construction. So, whatever that number is there, that will be coming in some kind of inches. That number if you convert into the mm, that is nothing but 0.074 mm. That has been taken as a kind of standard one, and then based on that one other screens have been designed. How they have other screens have been designed? So, let us say next the mesh number is larger, that means the aperture is the smaller. So, see, largest mesh number will have the finest opening. So, next opening whatever is next smaller opening whatever you have, like that you have to construct. So, there should be a kind of proper ratio should be maintained. So, in this particular screen what has been done, let us say this is one screen. So, we have seen that these screens are a kind of the constructed apertures, they are in the square size, right. So, like that you can take the next smaller one. So, here also you have this screen opening, let us say like this, right. Let us say this is 10 mesh, and then let us say this is 14 mesh. So, then whatever this the area of one particular square here let us in this 10 mesh, that you take this area, and then you take area of another, I mean any one square aperture of 14 mesh, right. If you take this area ratio, the area of this particular aperture divided by this area of this particular aperture, if you see, that will always be equal to 2. The area ratio will always be equal to 2 for this. This is how these meshes have been constructed. That is the reason after 10 mesh you will not be having the 11 mesh or 13 mesh, you will be having the 14 mesh. So, that we have a kind of standard series can be designed. So, this is how these screens are designed, right. So, this is the area ratio. If you take the dimension ratio, that is the this whatever the let us say dp1 here for 10 mesh, the screen aperture opening is dp1, and then 14 mesh, the screen aperture is opening is dp2. So, then dp1 by dp2 should be what? It should be square root of 2, because the area ratio is 2. So, then the dimension ratio should be square root of 2, because they are in the square shape. So, this is how the screens are constructed. Sometimes you may also need to have a kind of intermediate screens between these two. So, there are some kind of intermediate screens are also designed, so that whatever the ratio is there, let us say intermediate screen between dpi and then dpj is, let us say you have the intermediate screen. So, then that linear dimension would be having 4th root of 2, and the ratio between those two linear dimension, the regular one divided by the intermediate one, that value will always be 4th root of 2. So, this is how these Taylor standard screens have been designed. So, the area of the openings in any one screen in the series is exactly twice that of the openings in the next smaller screen, that is the area ratio is 2, or otherwise the ratio of actual mesh dimension of any screen to that of the next smallest screen would be square root of 2 or 1.41. Okay. For closer sizing, intermediate screens are also available, right. So, for which each of which has a kind of mesh dimension of 4th root of 2, that is 1.18 times that of the next smaller standard screen. So, this is the basis that Taylor standard screens have been designed, right. So, but in general intermediate screens are not used, they are used only for specified applications wherever the requirement is there, but in general they are not used. So, this is what the Taylor standard screen series. Now, we see different mesh number, what is the mesh opening, what is the diameter of the wire that has been used in a kind of tabular column. So, whatever these numbers, I mean like these symbols are there, they indicate a kind of intermediate screen. So, let us not go for them immediately. Let us say you have mesh 3. So, this opening should be 1 by 3, because per linear inch 3 apertures will be there, 3 openings would be there, right. So, that is the reason 1 by 3 minus the diameter used, wire diameter that has been used for constructing this 3 mesh is 0.07. So, that value is nothing but 1.333 minus 0.07. If you do, you will get 0.263. The same thing if you convert in mm, you will get 6.68, right. Let us say the mesh 4 is there. So, its opening should be 1 by 4 minus diameter of the wire that has been used 0.065 So, that is 1 by 4 is how much? 0.25, 0.25 minus 0.065 would be 0.185. So, the clear opening of that inches is having the dpi for that 4 mesh would be 0.185. If the same thing, if you convert in like mm, it is 4.699 mm. So, similar is mesh 5, that is the regular one. Now, if you take the ratio of this 4.699 divided by 3.327, you get 1.41, that is in the ratio of square root of 2. Similarly, 4.699 divided by 3.962, intermediate one if you do, you will get 1.189. So, that is how these standard screens are developed like this. So, any two successive mesh numbers you take and then you check the ratio, you will get the same thing, these numbers only. Likewise, all other mesh numbers like 65, 100, 150, 200 like that, 270, 325 are there. These are the kind of intermediates one with the symbol given here. They indicate for the intermediate screen, so that the ratio between these two, let us say here, that will be 1.189. Now, we do the size analysis. This the information, whatever the Taylor series is there, that screen opening information, that would be used as a DPI for each screen increment, and then DPI bar would be taken like DPI plus DPI plus 1 by 2, like that we take the average ones. Okay. So, that information we need, DPI bar information is required for the size analysis. That is the reason the information about these Taylor standard screens are important. So, that is how we got them here, right. So, now we see the size analysis of uniform mixtures. Uniform mixtures in the sense they may be any shape, irregular shape, but their size is the same, size and density of those particles is same, right. So, let us say you have a sample of uniform particles of diameter dp, then total volume of the particles would be m by rho p. Uniform mixtures here, they have the uniform size, dp is same for all the particles. Let us say you have glass beads of spherical shape. So, the diameter of each and every glass bead would be almost same, if not exactly the same, they will be almost same, close to each other. So, we can say that that particular mixture is a kind of a uniform mixture having the constant or the same particle diameter. Let us say the glass beads, all of them are having 1 mm. So, they will definitely be 1 mm or 0.995 mm or 1.005 mm like that. They are in the 1 mm range within plus or minus 1 or 2% error. So, the sample of uniform particles of diameter dp. So, then the total volume of the particle should be m by rho p. M is the mass of the sample and then rho p is the density of the particles. Then if the, let us say, particle is not spherical shape, it is having some other shape, then you need to know the sphericity of that particular particle shape also. So, for that reason we have this sphericity definition, pi s is equals to 6 Vp by Sp dp. Now, then if you wanted to know the total number of particles present in that particular uniform mixture, what you can do, you take the total volume of the sample m by rho p that you already know, divide it by the volume of single particle. So, then you will get the total number of particles. So, that is number of particles in the sample n is equals to m by rho p Vp. Vp is nothing but the volume of single particle, one single particle. So, the total surface area of the sample would be n number of particles multiplied by the surface area of one single particle. Since this mixture is a uniform mixture, you do not need to worry about the changes in the surface area from one particle to other particle, because all the particles are having the same size, same diameter. Then if you know the surface area of one particle, that particular value you multiply by the total number of particles, you will get the total surface area of the particle, that is n into Sp. So, n is number of particles, that is m by rho p Vp, and then Sp from this equation 1, what we get, Sp is nothing but 6 Vp by pi s dp. If you simplify it, you will get 6 m by pi s rho p dp as a kind of total surface area of the uniform mixture, whatever the uniform mixture that you have taken. So, that means if you know the mass of the sample and then density of the particles and then size of the one single particle, then you can know the total surface area using this one without worrying the other kind of information like what is the volume, what is the surface area, and then what is the difference from one particle to the other particle. You do not need to worry because of the uniformity of the mixture. Then if you have a kind of non-uniform mixture, how to do it? But before going to the non-uniform mixtures, we take a problem, example problem, uniform mixture, right. Size analysis of a uniform mixture. So, what we do? We calculate the total number of particles and then total surface area of uniform particulate sample consisting of spherical particles size 2 mm and density 2650 kg per meter cube, and then mass of the sample is 20 kg. So, what is the total number of particles and then what is the total surface area of the sample, because it is a uniform sample. So, you do not need much information other than these three. So, all information is given, sphericity is required, but that is also equals to 1 for spherical particles. So, simply we can get this information by using the equations. So, what would be the volume of the total sample? So, that would be m by rho p, m is given, rho p is given. So, total volume would be this one. Likewise, volume of one particle, because it is a spherical particle, the volume of one single spherical particle is pi d cube by 6, d is the size of the particle. So, then you get volume of single particle like this. If you divide the volume of total sample by volume of one single particle, you will get the total number of particles, 1801714 you get here. Likewise, the surface area of single particle is pi d square for spherical particles, that is given this one number, this number you get. Now, the total surface area of the sample that you can get by the multiplying these two numbers, that is total number of particles multiplied by the surface area of one single particle. When you do this, you get 22.641 meter square. Let us say you are not asked to calculate the number of particles, but directly only surface area of the sample if you need to calculate, you can use this equation directly. A is equals to 6 m by pi s rho p dp, and then substitute these numbers, you will get the same number 22.641 meter square in one single step. This we are doing because you also need to obtain the total number of particles. Now, what we do? We take another example. Here we take a short cylindrical particles of diameter 1 mm each rather than spherical particles, okay, and then density is same 2650 as the previous problem, but the mass is also is 20 kgs as the previous problem. So, only thing that we are changing the sample like now using a kind of short cylinders of 1 mm diameter and 1 mm height. If L is equals to D, then we can call those cylinders as a kind of short cylinders. Then mass of the sample, density of the sample is given. So, total volume of the sample would be m by rho p. So, then you get this number. Then volume of one particle would be pi d cube by 4 for short cylinder. So, that you get this number. So, the total number of particles is the total volume or the volume of total sample divided by volume of one particle. So, you get 9609141 particles, right. So, surface area of single particle for short cylinder with L is equals to D, we have 3 pi d square by 2, that comes out to be this one. Then total surface area of the particle will be the total number of particles multiplied by the surface area of single particle when you do this one. So, similarly, if you do not want to calculate the total number of particles, but you want to calculate directly the total surface area, so then you can use the equation A is equals to m by pi s rho p dp equation directly to get that information, but pi s is required. That for short cylinders we have already calculated it as a kind of 0.874. How we get dp we need to know. So, dp is you can get pi d cube by 4 of a short cylinder equated to the volume of a spherical particle size dp, which is the same volume as the particle volume. So, pi d cube by 4 should be equated to the pi dp cube by 6. So, from there dp you get 1.1447 d. At the time of calculating sphericity, we have also seen that the sphericity does not depend on the size of the particle. So, without substituting their true volume or the true surface area etc., we can directly substitute their formulas and get the results. But however, this will be a kind of demonstration that even if you substitute the true volume and then surface area of the particles, you will get the pi s is 0.874. This shows that it is independent of the size anyway, right. Then you substitute A is equals to 6 m by pi s rho p dp here. So, then you get 45.262 meter square anyway. So, this is how the size analysis of uniform mixtures one has to do very simply without worrying too much. But coming to the sample of non-uniform particles, so the analysis could be slightly different or a bit a lengthier process than what we have done. Okay. Uniform mixtures, particles are same size, so then you can do as a one single fraction. But here non-uniform mixture, the particle size distribution may be very wide. So, what you do the screening and then divide it into the different fractions. Each fraction may be having the more uniform particle size distribution, so that you can assign one average diameter. So, one average diameter would be assigned to one fraction, another average diameter would be assigned to the another fraction. Like that you can assign different fractions, different average diameters, and then for individual fractions you can use the principles of same uniform mixture size analysis of uniform mixture principles, because individual fractions now they are treated as a kind of uniform. They are not uniform, but the size range, variation in size range is very narrow, that you can assign one average diameter. So, then for individual fraction you can apply the principles of the size analysis of uniform mixtures. Like that you have to obtain the surface area of individual fraction of all fractions indeed, and then add them together. So, then you get the surface area of the entire sample. Okay. If you divide by the mass of that entire sample, then you will get the specific surface of the entire sample. That is how we have to do. But here the non-uniform particles, we have two approaches for reporting the results or obtaining the some kind of size analysis results. One is the differential analysis, which is also known as the fractional analysis. Another one is the cumulative analysis. In the differential or fractional analysis, whatever the samples of particles having various sizes and densities, mixture is divided into fractions by doing this screening operations, as we have discussed before. Then each fraction is of constant density and approximately constant size, not the constant exactly same size. Each particle will not have same size within each fraction, but approximately constant size. So, dpi bar can be assigned, right. Each fraction is then weighed, or the individual particles in it can be counted by n number of methods available. Okay. Then following two equations can be used for each fraction and the results are added. What are these equation? Ni is equals to mi by rho p Vpi, the same as exactly the uniform mixtures. There we do not have this subscript I indicates the screen increments, right. I can be 1 to 20 if you have the 20 screens, I can be 1 to 10 if you have 10 screen increments within this take where you have done the fractionation of this sample into individual fractions, right. For ith screen increment, number of particles would be the mass of the sample that has been retained on that particular screen divided by the density of one single particle that is retained on this particular sample. So, in this VPI we do not use like individual particle diameters of that one, we take the average diameter, that is dpi bar for that increment that we take in order to get the volume of single particle. So, similarly the surface area of the sample retained on particular screen increment I would be the Ni into SPI, that would be 6 mi by pi s rho p dpi bar. So, now this here it is not dp but dpi bar, the average diameter of sample, that whatever that ith increment is having is retained on that ith increment. Then these equations are a kind of purely for individual fractions, they are not for the entire non-uniform mixtures. So, basically non-uniform mixtures, what we are doing, non-uniform mixtures we are subdividing into several fractions, but each fraction is almost a kind of uniform mixture, that is it. And then for each fraction we are applying the principles of uniform mixture, and then we are adding them together in order to get the numbers, required number for the entire non-uniform mixture. So, if specific area of sample is to be obtained for that non-uniform mixture, then that the AI should be divided by the whatever the total mass of the non-uniform mixture. So, then that you do. So, small mi by capital M, let us say capital M is the mass of the total sample, that should be kind of mass fraction. And then for a given fraction, individual fraction, in general the sphericity may remain same and then particle density may also be same. So, then those things may be separated out. If they are not same, then they should be kept inside the summation. Okay. So, individual fractions whatever are there, AI whatever there, all the AIs are added together and divided by the total mass of the sample, so that we get the specific area of the non-uniform mixture. Then whatever the mass fraction versus average particle size, the information you get, that can be plotted like a histogram like this shown here, or they can be plotted like a kind of graph as shown here. So, you may get the distribution like this for non-uniform mixtures. Then coming to the cumulative analysis, here it is obtained by consecutively adding individual increments starting with that containing smallest particles and plotting cumulative sums against the maximum particle diameter in the increment. What we have, let us say we have these many increments, let us say this I is equals to 1 for the pan, I is equals to 2, like this we have I is equals to 3, 4, 5, 6, 7. Now, there would be some material retained on each of these things, screens including the top one also, based on the screen analysis that we do, and then based on the size of the nature of the sample, and then other properties of the sample, okay, and screen opening etc. So, whatever the material that has been retained on this one, you assign some fraction x I or x 6, this is x 7, this is let us say x 5, x 4, x 3, x 2 and x 1, let us say. The screen opening here is dp 7 for the 7th one, likewise dp 6, dp 5, dp 4, dp 3, dp 2 and this is actually pan, so it should be 0 opening. So, now cumulative analysis, what we do for dp 7 row, the cumulative fraction x 7, what is the fraction of material that is having the opening, or that is having the size smaller than dp 7, right. So, this is cumulative analysis actually in two types, cumulative oversize, undersize, right. Undersize we will say like dp 7 first we take, so in the column here. So, how do you find for against the dp 7 cumulative fraction should be what? So, against to x 7 the cumulative fraction smaller than dp, let us say. This is dp. So, first one is dp 7. So, like this dp 8 and then here you have this xi, x 7, s 6, dp 5, x 5 and so like this. So, now here what should be the number here? The cumulative fraction smaller than dp 7. So, this is dp 7 having fraction x 7 and then dp 6 and all of them dp 5 are having the smaller opening, because the coarsest one is at the top we arrange screen such a way. So, now the whatever the fraction other than this column, this entire thing whatever the things are there, they are all having size smaller than dp 7, dp 6, dp 5, dp 4 and all that are having size smaller than dp 7, dp 7 is the largest one. So, this fraction, the value should be here x 5 plus x 5, x 6, x 4 and plus x 3. So, that is x 6 plus x 5 plus x 4 plus x 3 plus x 2 plus x 1. Likewise, here when you come to here, you come to this point, what is the fraction of material which is having the size smaller than dp 6? So, dp 5, dp 4, dp 3, dp 2, dp 1, all of them are having the size smaller than dp 6. So, then corresponding fraction should be added here cumulative, that is x 5 plus x4 plus x3 plus x2 plus x1. Likewise, here it should be x4 plus x3 plus x2 plus x1. Like this we have to add, and then this cumulative fraction versus dp one has to plot. That will give the cumulative fraction or the cumulative analysis smaller than dpi, right. Like that we can do the exactly the other reverse one, the cumulative fraction larger than dp. If you do the larger than dp here, so this case it should be 0, this case should be x7, this case should be x6 plus x7, like this we have to do. Let us say cumulative fraction larger than dp. We take example problem also, so I am just explaining here. So, it will come like this, okay. It will be opposite to the other one. So, this is how we have to do the cumulative analysis. So, plotting cumulative sums against the maximum particle diameter in the increment is a kind of gives the cumulative analysis. This cumulative analysis one can plot on a log-log or semi-log plot as well. And then size analysis from a crusher or a grinder often give linear plots on log-log or semi-log papers. On log paper, if you get a straight line by this cumulative analysis, then whatever the differential analysis results are there, that you can obtain by just linear interpolation. You do not need to worry about the other details, right. So, this is how we have to do the cumulative analysis, right. So, cumulative undersize and oversize analysis, if you see, so this is whatever the way that mass fraction xi versus particle size dp, if you plot, or dpi if you plot, the ones that I have drawn here, this is what we have done. Cumulative fraction smaller than dpi would be like this, and then cumulative fraction larger than dpi would be like this. So, they are opposite to each other. This is undersize, cumulative undersize analysis, this is cumulative oversize analysis. Now, we take an example problem. So, let us say fractional and cumulative analysis, we take this example problem. We have the mesh screen plus 10, minus 10, plus 14, minus 14, plus 20, like this, screen openings, I mean mesh numbers are there, that is what they are arranged. That is means at the bottom they have the pan, above it they have 65 mesh, above it they have 48 mesh, above it they have a 35 mesh, above it 28 mesh, like that. At the top 10 mesh is there, right. Whatever the material retained on 14 mesh, that should be minus 10 plus 14. So, what do you mean by minus 14 plus 20? The material that is passed through 14 mesh, but retained on the 20 mesh, like that their corresponding mass fractions are given. So, 14 mesh, 10 mesh, their dp, the screen openings from the Taylor screens we have already seen, right. If you take the average of those dp's, let us say what is the dp of 10 mesh plus what is the dp of 14 mesh divided by 2, then you get this number 0.0555 in inches, they are in inches, like that. Other averages also like this. So, or for simplicity I write dp 10 plus dp 14 by 2 is this number. This number is dp 14 plus dp 20 by 2, that is screen opening of 14 mesh plus screen opening of 20 mesh divided by 2, arithmetic average. So, all these average diameters dpi bars are given, then mass fractions are given, right. So, now cumulative fraction smaller than dpi bar, here see the average diameters are given. So, we do in a kind of dpi bars, but they should be in general done with respect to dp, okay. So, now first one, what is the cumulative fraction smaller than dpi, what is this, actually this size would be more than 0.055. So, smaller fractions, if you see what is the fraction of material that is having size greater than 0.055 or smaller than 0.055, not greater than, smaller than 0.055 is like this, all these fractions. So, all this is 0.0555, this thing, all these things are smaller sizes. Their corresponding fractions or they should be added and then written here. Likewise, now for this let us say we do the second one. What is the fraction of material which is having size less than 0.0555? This is let us say, I repeat once again. Let us say the size opening the average diameter, not the average diameter, for mesh 10 the screen opening is 0.065 inch. So, what is the fraction of material whose size is smaller than 0.065? So, all this material 0.0555, 0.0394 etc., all of them their sizes are smaller. So, then corresponding fractions whatever are there, they should be added and then reported here. So, 0.02 plus 0.05 plus 0.1 plus 0.18 and so and so, you will get 1 here. Similarly, in the second row here, what is the fraction of material whose size is smaller than 0.0555? So, this 0.0394, 0.028 and all of them are smaller than 0.0555. So, their corresponding fractions whatever are there, so they should be added together and then written here. So, that is 0.98. Likewise, the third row, what is the fraction of material whose size is smaller than 0.0394. So, all these 0.028, 0.018, all of them are having smaller size compared to the 0.0394. So, these fractions whatever are there, they should be added together and written here. So, that is 0.093. Like that we have to construct all of them. And then same in the similar way we have to do cumulative fraction larger than dpi here. So, now 0.065 first row, what is the fraction of material whose size is larger than 0.065? There is nothing, so 0. See, the fraction of material whose size is more than 0.065 is 0, so that is 0. What is the fraction of material whose size is more than 0.0555? So, there is no fraction here, so again this one is also 0. What is the fraction of material whose size is more than 0.0394 is only 0.0555 is more than 0.034. So, only this 0.02 should come here. Then next one is what is the fraction of material whose size is larger than 0.0280. So, only two fractions are there, 0.0394, 0.0555 are the larger one, their corresponding fractions 0.02 plus 0.05, that should come here 0.07. Likewise, we have to construct all of them. Then you can plot them. So, when you plot cumulative fraction smaller than dpi versus xi, you will get plots like this. This is cumulative fraction smaller than dpi, this is cumulative fraction larger than dpi. This fractional distribution, this anyway we have already done. Now, if you wanted to know the average particle size, specific surface area and particle population, then we need to do some kind of calculation. So, the calculation of average particle size, specific surface area or particle population, that is number of particles, may be based on either fractional or differential analysis or by the cumulative analysis. However, the methods based on the cumulative analysis are more precise than based on the differential analysis, because the differential analysis has assumption of equal particle size in particular single fraction. Within the single fraction, whatever the material is there, that we are assuming that it is having a kind of uniform diameter, but those kind of assumptions are not there in the cumulative analysis. That is the reason if you get the numbers using the cumulative analysis, it would be more precise. The cumulative analysis may be found from the sieving test as well, and they can be plotted on the straight lines. Okay. By differential analysis, we do specific surface of non-uniform mixture calculations. How to do that one? So, surface area of particles in each fraction, let us say pi s rho p are known. Okay. Then the surface area of particles in that particular given fraction would be number of particles multiplied by the Sp, that is the surface area of those particles. So, then that comes out to be 6m by pi s rho p dp. It is same as a kind of uniform mixture, but it is valid only for individual fraction. Now, specific surface is the total surface area of a uniform of a unit mass of particle. So, specific surface is the total surface area of a sample per unit mass of the particles or whatever the sample that you have taken. So, this A, if you divide by m and then add them together for all the increments, this is for one increment. Like that you have all increments, screen increment, let us say this is for screen increment 1, this is for screen increment 2 and so on. So, this is nth screen increment. So, if you add them together and then pi s rho p, you assume the same for the entire mixture. So, 6 by pi s rho p sigma xi by dpi bar, because 1 by capital M is x1, m2 by capital M is x2, like that all xi's are there. So, xi by dpi bar. So, here xi x1 by dp1 bar plus x2 by dp2 bar and so on. So, we can write it as a summation of xi by dpi bar. Sometimes this pi s rho p may not be same for a given fraction, individual fraction. So, they should also be brought into the kind of a summation. Let us say you have a kind of a non-uniform mixture, but different types of particles like spherical particle, short cylinder particle, cubical particle, like that, then pi s would be different for each type of particle. So, then that should be taken inside the summation. So, this is how you can get the specific surface of a non-uniform mixture, that is the total surface area of the mixture divided by the mass of the sample. Here xi is the mass fraction in a given increment, n is the number of increments, how many increments that you have, how many screens that you arrange in the experiment, 1, 2, 3, 4 up to 10 or 20, that number is indicated by the n. dpi bar is the average particle diameter, that is the arithmetic average of smallest and larger particle diameters in respective increments. Then average particle size of mixture defined in several different ways. Actually, it is not possible to define them in one single way. There are several types of ways available, okay, and then all of them will give a different value. So, selection of that which average value should be taken, that again comes with the experience, and then from process to process where the samples are going to be used. The first one is volume surface mean diameter. It is related to the surface area AW as given by ds bar is equals to 6 by pi s AW rho p, right. So, here AW we have already calculated, we have seen for a non-uniform mixture, that you substitute here, then this AW is 6 by pi s rho p sigma xi by dpi bar, that just now we have seen, you substitute here and then simplify. So, you will get ds bar is equals to 1 by sigma xi by dpi bar, right. So, this is the volume surface mean diameter. It is also known as the Sauter mean diameter. Sauter mean diameter is the one of the reliable one compared to the other one for most of the applications, however, not for all the applications. And then this average particle size of mixtures, you calculate either if you know the mass fraction of the material retained on that particular increment, or if you know the total number of particles in that particular increment. Let us say for each increment, rather mass fraction, if you know the number of particles, how to get this volume surface mean diameter or Sauter mean diameter, that we will see. So, this is if you know what is the mass fraction of the material on each increment. In place of xi, if you know the ni, that is the total number of particles in that fraction, then you have to use this equation. ds bar is equals to sigma ni dpi bar ai divided by sigma ni ai. So, here this ai is nothing but the surface area is there. So, that particular thing is there. So, usually it is dpi bar square multiplied by some surface area shape factor would be there. Let us say if the particles are spherical, then this b the surface area shape factor whatever is there, that would be pi. Let us say if you have a short cylinders, L is equals to D, then this surface area shape factor b should be 3 pi by 2. So, that is that particular multiplication factor of that dp. So, that may be different, and then for non-uniform mixtures you cannot have one single value. So, but that is the reason we are assuming that, let us say that constant is B, and then it is same for all the particles within that particular mixture. So, that is this one. So, when you substitute here also AA like this and then simplify, you get sigma Ni dpi bar cube divided by sigma Ni dpi bar square is nothing but the volume surface mean diameter ds bar, and this ds bar is also known as the Sauter mean diameter. Arithmetic mean diameter dn bar is equals to sigma Ni dpi bar by sigma Ni. So, sigma Ni is nothing but Nw, that is the total number of particles in the sample. Likewise, mass mean diameter, you have dw bar is equals to sigma Ni dpi bar mi divided by sigma Ni mi. So, Ni is nothing but xi by rho p Vp. Actually, this Ni is mi by rho p Vp. Mi by rho p is the volume of the all particle present in that particular increment, ith increment, and then Vp is volume of one single particle of that particular sample for that taken from that particular increment. So, here, but we are doing kind of per unit mass of the sample. So, if you divide by capital M, so you get xi by rho p Vp. So, xi rho p and then Vp is nothing but A dpi bar cube. The average diameter of the sample, that particular sample for that given increment is dpi bar. So, volume should be some constant multiplied by dpi bar cube, that constant is A, or the shape factor, volume shape factor A, like B is surface area shape factor, A is volume shape factor. Okay. And then this dpi bar is as it is. Mi is nothing but rho p into that volume of the particles, whatever the single particle is there. So, that Mi is rho p multiplied by the volume of the all the particles in that particular mixture is A dpi bar cube. Okay. Like that, here also Ni you substitute and then Mi you substitute, then you simplify, you get sigma xi dpi bar divided by sigma xi, and then sigma xi is nothing but 1. Summation of all mass fractions is 1 for a given sample. So, mass mean diameter dw bar is nothing but sigma xi dpi bar, whereas the volume surface mean diameter ds bar is nothing but 1 by sigma xi by dpi bar. Like that, we can have the volume mean diameter dV bar is equals to 1 by sigma xi by dpi bar cube whole power 1 by 3. So, as I already mentioned, for a given mixture containing particles of various sizes, then there will be several average diameters and they may be different widely from one another. Let us say for a given sample, you do the analysis and then you obtain the ds bar, you obtain the dV bar, and then you obtain the dN bar, and then you obtain the dW bar. So, all 4 types of average diameter you calculate, all 4 of them may be giving different numbers. So, one should be careful based on the application which number should be selected, which could be the most appropriate. So, derivation of volume mean diameter we can see, because the ds bar, dN bar, dW bar we have seen in a simple way. So, the similar way it is difficult to do volume mean diameter, but the other way we can do. The total volume of all particles should be the volume of mixture, and then total volume of all particles should be the total number of particles multiplied by volume of single particle, but that volume calculated using this volume mean diameter dV bar. So, that is A dV bar cube sigma Ni. Sigma Ni is the total number of particles in the sample, and then volume of single particle having the average diameter volume mean diameter dV bar should be dV bar cube multiplied by the volume shape factor A. So, A dV bar cube sigma Ni. Then volume of mixture, so now should be sigma A dpi bar cube Ni. So, this is for each individual increment you know the dpi bar. So, for each increment what is the volume that you know, for each increment what is the number of particles Ni you know, you multiply them and then you do the summation for all the increments. So, that is what this one, this is dpi bar is that average diameter for that increment, for that screen increment, whereas dv bar is that the volume mean diameter for the entire sample, right. So, that means all the particles we are assuming that they are having a mean diameter, volume mean diameter of dv. Okay. Whereas coming to the mixture, we are assuming that all the particles are having the average diameter of dpi bar for a given ith increment. Okay. So, when you equate these two now, you will get dv bar like this, and then here you substitute Ni is equals to xi by rho p Vp, then rho p is as it is, Vp is nothing but for a given increment, ith screen increment a dpi bar cube, right. So, that you substitute in the above equation here, Ni wherever this Ni and then this is sigma Ni, and then do the simplification, you will get 1 by sigma xi by dpi bar cube whole power 1 by 3, or cube root of 1 by sigma xi dpi bar cube is nothing but volume mean diameter. Then number of particles in mixture already we have discussed, that is mi by rho p Vp for one particular fraction. Total number of fraction would be Nw, that should be mi by rho p Vp summation over mi by rho p Vp if you do the total number of particles for a given mixture. And then for a given particle shape factors, let us say Vp is equals to a dp cube. So, a is the volume shape factor. As I mentioned, for spheres it is pi by 6, that is 0.5236, that is if the particles are spherical in shape, then A is pi by 6, as I already mentioned before. If the particles are kind of short cylinders, then A is 0.7854, that is pi by 4. If it is cubical particle, then A is equals to 1, and then assuming A is independent of size, then Nw you can calculate using this expression if you know the volume mean diameter dV bar. So, now we take an example. Screen analysis of a crust sample is shown in table. The density of particles is 2650 kg per meter cube, whereas the shape factors are 0.8, and then that is whatever the shape factors are there 0.8, and then sphericity is 0.571. For the material between 4 mesh and 200 mesh in particle size, calculate AW, that is specific area of the sample in mm square per gram, and then NW in particles per gram, that is total number of particles per gram of the sample. Then also calculate the volume mean, Sauter mean and arithmetic mean diameters. Also calculate Ni only for the 150 by 20 mesh screen increment, not for the entire sample, only for that particular increment. Then what is the fraction of total number of particles is in the 150 by 20 mesh increment. That is actually, we see the table here, this is the information, 150 by 20 mesh is this one. So, that is excluding the pan, whatever, I mean what are the finest particles are there, that we are going to calculate anyway. Screen increment I and then mesh number are given. In screen increment, we in general give the largest number at the top and then smallest first number at the pan, for the pan. So, pan is 1, 2, 3, 4 like that. So, 14 increments are there. The finest mesh that is used 200 mesh, that is at the bottom, and then coarsest mesh that is used is the 4 mesh, and that is at the top. Their corresponding opening DPIs are given here. So, they are not DPIs. DPI bars, they are DPI only. So, mesh 4 is having the screen opening of 4.699 mm, and then their corresponding mass fractions. Let us say what is the mass fraction that is retained on 4 mesh is 0, what is the mass fraction that is retained on screen or mesh 6 is 0.0251, like that all these things are given. So, now we need DPI bar, average diameter. So, average diameter is, first one is nothing as it is, or 4.699 one can write because it is only 1. So, the second one is the average of these two, that is 4.699 plus 3.327 divided by 2 So, you get 4.013. So, likewise all the other diameters, average diameters also. So, cumulative fraction smaller than dpi here. So, no, dpi here is 4.699. So, we are doing only smaller one. So, what is the fraction of the material whose size is smaller than 4.699 mm? So, all these 3.32 onwards, all of them are having smaller than 4.699 mm. So, their corresponding mass fractions, all of them should be added and then written. So, that is one. Next one is, what is the fraction of material whose size is less than 3.327. dpi is now here in for this row 3.327. So, except these two, all other things are having the size smaller than 3.327. So, all the corresponding fractions, this one from here to here, we have to add together. So, that comes out to be 0.9749. Likewise, what is the fraction of material smaller than dpi 2.362, right? Except these three, all other these are smaller than 3.262. So, their corresponding mass fractions are this one 0.3207 plus 0.2570 and so on, so 0.0075. If you add them together, you get 0.8499. Likewise, we have to construct all of them. This will give you cumulative fraction smaller than dpi. So, the first part of the question is obtaining the AW. AW is 6 by pi s rho p sigma xi dpi bar. So, here in this table we have xi, for each you have to have the another column xi by dpi bar here. So, whatever the xi, this xi and then corresponding dpi bar here. So, that should be 0. So, here it should be 0.0251 divided by 3.327, like that all the values we have to have here and then we have to do the summation. When you do that one, you get this particular sigma xi dpi bar. So, remaining fractions are 0.3965. The 6 by pi s rho p is having 3965 value. Similarly, NW is 1 by a rho p sigma xi dpi bar cube. A is also given as 0.8. So, 1 by a rho p is 471.7, and then here in this one we have to have another column xi by dpi bar cube. So, this one also you do the similar one and then do the summation, whatever the value is there that you should put here, that will be giving us the numbers. But the question is that total number of particles between 4 mesh to 200 mesh. So, whatever the particles they are present in the pan, they should not be considered, they should be excluded. When you exclude them, so you get the true number of picture, otherwise you get the different number. So, whatever the pan fraction is there 0.0075. So, 1 minus x1, x1 for the pan. So, 1 minus 0.0075 is 0.9925. So, whatever these numbers are there, if you divide by 0.9925, you will get the true numbers, that is AW is 3309 mm square per gram and then NW is 4196 number of particles per gram, right. Here this densities etc. they have taken in the gram per mm cube, because we want to report these values mm square per gram. Also in the question it is mentioned to report them in mm square per gram. So, similarly average particle diameters, we have ds bar is equals to 1 by sigma xi dpi bar. So, for each row you obtain what is xi by dpi bar and then add them together and then you take the reciprocal of that one, you get 1.207 mm. Likewise, for each row in the table you calculate what is xi by dpi bar cube and then you add them together for all the rows, then you take the reciprocal of that and then you take the cube root of that one, you get 0.4838 mm. And then mass mean diameter, for each row you get xi multiplied by dpi bar and then for all the rows you do like that and calculate them and then add them together, you get 1.677 mm. Now you can see all 3 numbers are very much different from each other, not even close to each other. The number of particles in increment 150 by 20 mesh is 1 by A rho p x2 by dp2 bar cube, because that is 150 by 20 increment is nothing but I is equals to 2. So, n2 is equals to 1 by A rho p x2 by dp2 bar cube. So, when you substitute these things, you get 2074 particles per gram. So, in the pan we have this many particles. So, the fraction of total number of particles in 150 by 20 mesh is nothing but this 2074 divided by 4196, that is 50%, 49.4, almost 50% of the particles are in 150 by 20 mesh increment. So, that indicates that the sample is having so many finer particles, almost 50% of the sample is having finer material. Okay, this is how one has to do the problems. So, we take one example where we do not take the screen analysis results, but we have a mixture of different types of particles. We take, let us say, 10% of spherical particles, 20% of the hemispherical particle, 30% cylindrical particles and 40% cubical particles. That is a kind of non-uniform mixture we have, but the density is same for all of them, and then particle shapes are also given. Diameter for spherical particle is 2 mm, and then short cylinders 1 mm, and then hemisphere 0.5 mm, and then cube is 0.1 mm each. So, for this what we need to do, we have to find out the sphericity for each particle type and then obtain specific surface of the sample. So, particle size is given mm, and then corresponding mass fractions are given here in this second and third column. Okay. This is the summation. When you add together, this fraction is 1. So, Vp, the area of particle, each particle, and then Sp, the surface area of each particle is calculated here. So, dp by d if you do that, you will get here, and then pi s I, we already know that it is spherical particle 1, and then cylindrical particle, this this particle diameter, if you equate to the particle volume, if you equate to the volume of a spherical particle whose diameter is dp. So, then that dp you can use the sphericity definition. So, you get 0.874, this anyway we have already calculated. So, this pi s is nothing but 6 Vp by dp Sp, 6 by dp by Sp by Vp, that is 6 Vp by dp Sp when you do for spherical particle 1, and then for this short cylinders 0.874, this hemisphere 0.84, and then cube 0.806. These things we have already calculated in one of the previous lecture. The specific surface area here is 6 by rho p sigma xi by pi si dpi. Now, the sphericity is different for one particle increment, one fraction to the other fraction. So, that pi si is coming into the summation. So, you have here pi si dp, you already dp you calculated here. So, now pi si you calculated, you can get pi si dp as 6 Vp by Sp. So, you get these numbers. Now, xi by pi s dp, you get these numbers, you add them together. So, you get 4.8. So, 6 by rho p is 0.00265 gram per mm cube multiplied by sigma xi by pi si dpi is 4.8. So, that gives us 10867.92 mm square per gram. This is how we have to solve the problems related to the non-uniform mixtures. So, now we take another example problem, example 6. Here what we do, we see the project size distribution of a sample obtained by screen analysis given in a table, like mesh number 8, 10, 14, 20 and so on, so up to 200 pan it is given, and their corresponding screen opening in mm also given along with their mass fractions. So, screen analysis has been done using the screens between 8 to 200, and then whatever the mass fractions or mass retained on each of the screen have been converted into the mass fractions, and then they are reported against individual screen increments. So, we have a screen increments from pan to 8 mesh in an increasing order, right. So, the question is, draw the undersize and oversize cumulative analysis. and then calculate specific surface of the sample and total number of particles. Also obtain volume surface mean, mass mean and then volume mean diameters of the sample. It is quite similar as one of the previous problem that we have already seen, but in addition to that problem we have to draw the undersize and then oversize cumulative analysis as well. So, for this problem the shape factor and then sphericity required, which are given here 0.78 and 0.874 respectively, and density of the sample is 2700 kg per meter cube. So, let us tabulate this information in a kind of sequential order, incremental order, mesh number 8, 10, 14, 20, 28, 35, 48, 65, 100, 150, 200 pan, and then corresponding openings in mm that is given in the problem, or if it is not given we can take them from the Taylor standard screen openings. Okay. Then corresponding mass fractions excise are given 0, 0.03, 0.14, 0.25 and so on, so 0.005. If you add them together all, you will get summation 1. So, the last row provides the summation wherever it is required. So, we need to have a DPI bar, that is the average diameter for each increment. So, for this case first one there is no kind of average diameter because it is the first one. So, whatever the material that is retained, that has been taken as the mass fraction, but however there is no material retained also as per the mass fraction given. So, we need not to worry about this one. Actually it is not 0, it should be taken 2.362 if required. So, but it is not required as of now anyway because there is no mass fraction retained on this particular 8 mesh. Next one is DPI bar for the second row is the average of these two values, that is 2.362 plus 1.651 divided by 2, that you will get 2.0065. Likewise, this DPI bar would be the average of these two, this DPI bar would be the average of these two, and then this DPI bar is the average of these two numbers. Likewise, you construct all of them. So, let us say this DPI bar 0.037 you get by taking the half of this one, because here now pan it is not having, for the pan the opening is 0. So, whatever 0 plus 0.074 by 2, that is 0.037. So, like that all the DPI bars we can include here. Now, the first part of the question is the cumulative undersize and then cumulative oversize plots we have to give. So, undersize we see first. So, undersize in the sense the fraction of material smaller than DPI. So, for this case DPI is 2.362, right. What is the fraction of material that is having size smaller than 2.362? So, all these values like 1.651 to all these 0.074, all these screen openings are smaller than screen opening 2.362. So, what is the summation of the corresponding mass fraction? So, all these mass fractions whatever are there, so they should be taken. So, when you add them together you will get 1. So, that is what this one. Next one is what is the fraction of the material whose size is smaller than 1.651. So, except this 1.651 itself and then 2.362, all other fractions, all other openings are the smaller than 1.651. So, the corresponding fractions whatever are there, if you add them together you will get the value that should be entered here, that is 0.97. Likewise, what is the fraction of material whose size is smaller than DPI? Here DPI is 1.168. So, except these 3 top ones, all other screen openings given from mesh 22 pan or mesh 200, all of them are having screen openings smaller than 1.168. So, the corresponding mass fractions 0.25 onwards to 0.005, if you add them together whatever the number is there 0.83, that you get here. Likewise, the fraction of material smaller than DPI 0.833 would be 0.58 if you add them together these numbers, and then fraction of material smaller than DPI 0.589 would be the summation of all these numbers 0.14 to 0.005, all of them add together you get this number. Like that you can get all these numbers here by finding out their cumulative fractional smaller than DPI of that particular row, that is that particular mesh. Okay. now we take cumulative oversize. So, now for the first row what is DPI 2.362, what is the fraction of material whose size is more than DPI 2.362? Anything is there? There is nothing because the maximum courses opening is 2.362.